All right, so I want to pick up where we left off yesterday. We talked about yesterday how we reflect a graph across the x-axis, okay? I want to talk a little bit about how we reflect it across the y-axis, okay? And this is usually a little bit more of a difficult procedure, but nonetheless, it's something that we should be able to do. If we take myself a little bit more room here. If we take a function, let's say like, and I'm not going to ask you to do this a lot because it is confusing for some people. But if I take like f of x equals, let's say that I've got a function that looks like, we'll just go x cubed is the, well, that's not going to work. X, let's do it this way. If I go x, like plus 3 squared. Okay, if I start with that function, so we know from what we've talked about in the last couple days, x squared is what we refer to as the parent function. Okay, so if I were to graph x squared, we have the point 0, 0, we'll have the point 1, 1, we'll have negative 1, 1, and we'll have 2, 4, and we'll also have negative 2, 4. Okay, so those are the points for x squared. Does that make sense? Okay, so I'll just graph that as f of x equaling x squared. Now, if I were to look at what f of x equals x plus 3 squared looks like, all it does is it takes these points that we've created over here and it moves them 3 units to the left. Okay, so when you add to the x, it's going to actually move every x value to the left. So this point here at negative 2, 4 is actually going to go to negative 5, 4. Okay, this one here is going to go at negative 1, 1 is going to go to negative 4, 1. This one here is 0, 0 is going to go to negative 3, 0. So all we're doing is subtracting 3 from all of these x values. So 1, 1 is going to go to negative 2, 1. And 2, 4 is going to go to negative 1, 4. And we get that graph. Does that make sense? Okay, so we talked about that last couple days. Now, if I were to put a negative out in front, and this is what we talked about yesterday. If you take a negative out in front, what that's going to do is it's going to take this graph right here, and it's going to flip every one of those points across the x-axis. So it's going to come down here. That point, obviously, is on the x-axis, so it stays. But this point's going to go down to negative 1. That one's going to go down to negative 1. These up here that were at a height of 4 are going to go down to a height of negative 4. 1, 2, 3, 4, right there. And this one's going to go down to a height of negative 4. And we get that blue parabola. Does that make sense? Everybody remember that from yesterday? Just kind of demonstrating this real quick in this program. Our parent function was x squared. Okay? If I take it and add 3 to it, it moves it over to that blue one, right? Take that blue one and multiply everything by a negative, and it reflects the blue one to become that orange one, right? Does that make sense to everybody? Okay. So that's nice, but let's talk about what happens when we take our x plus 3, x plus 3, come on, squared, which was that graph right there. And if I put a negative in front of it, so it would look like that. Putting a negative in front of it reflects it over the x-axis, right? Okay. Now, I'm going to change the position of the negative. I'm going to put the negative inside with the x. So the way that would look is if I go f of negative x like that. Do you see how it put the negative on the inside now? You see the difference? Okay. So if the negative is on the outside, it's a reflection across the x-axis. If the negative is on the inside with the x, what's it reflecting across? The y-axis. Okay. So the positioning of our negative is going to tell us whether we reflect across the x-axis or reflect across the y-axis. The way I remember it is whenever you do something to the x. So in this one here, h, if I was to create a table of values, okay, for x and comma h of x, you would choose an x value like maybe 3. And you would have to, before you squared it, before you ran it through what the parent function tells us to do, you would actually have to take that 3, make it negative first, right? And then add 3 to that before you square it. So if you have to do something to the x before you square it, that tells you that there's going to be a change in the horizontal positioning. It's either going to, so this plus 3 is going to move it left 3, and because that negative was to the x before I squared it, it's going to be a reflection horizontally, and that's what we're seeing here, is that this purple one reflected horizontally over here to this red one. That kind of makes sense? Okay, it's, I think, a difficult analysis for students to recognize that the positioning of that negative then dictates how either the x or the y is being impacted. In this case, the x is being impacted. Here, the y is being impacted. So that's why we get those different reflections. All right, so that's a horizontal reflection. I want to talk now about maybe, like, I think the vertical movement is maybe the easiest transformation because instead of adding or subtracting the whole thing, it just changes the y's. I think the second easiest is dealing with a vertical stretch or a vertical compression, okay? And all this is talking about, do you guys remember in geometry where you would take a shape? Let's say we have like a triangle like that, and I ask you to, you remember the word dilate? Okay, so if I take this shape and I dilate it on that point by some factor, and it's called factor C, and, oh, not C because it's being used somewhere else. Let's do this. Control Z, come on. All right, rename D. There we go. All right, so if I take this triangle and I dilate it by a factor of 2, it grows into that triangle. You guys remember doing that last year? Okay. And now I'm going to ask you, well, how does that point there of B, which is at 10, 4, how does that correspond to B prime? How do those two things relate? Well, if I look at those two ordered pairs, how is this ordered pair, how is B prime different than B? It's double, right? Okay. Now in this situation, we doubled both the x's and the y's. Okay. But that's a dilation. When we talk about what we call a vertical stretch or a vertical compression in algebra, it's the same idea. The only thing that changes is the y value. Okay. So here we got the rule here. It says the notation says y equals f of x. Then when you take y equals c times f of x, you're going to multiply by some number out in front. Multiply by some number out in front of your function. If c is bigger than 1, it's called a vertical stretch. So think about, take a number. Get a number in your head, any number you want. Okay? Now, multiply it by 2. What happened to that number? Did it get bigger or did it get smaller? Got bigger, right? Because 2 is bigger than 1. Take that same number, multiply it by 3. What just happened to that number? Bigger or smaller? Bigger, right? Okay. So what we're saying here is this y equals f of x. Remember, this is a rule. It might be like x squared that tells you what a y value is. Okay. But if I take that y value and I multiply it by something bigger than 1, then that y value just got bigger, right? So what happens is that we get what we call a stretch. So if we look at this example here, okay, and I'm just going to do the table here, and we'll go to GeoGebra to actually analyze the graph. But if I go x and then f of x, 4x squared, okay, so that's a parent function that we know has those x values. And if I look at the y values that go with those, just square these, I get 4, 1, 0, 1, and 4, right? Okay. So we could graph that, and we will when we get to GeoGebra in a minute. But now let's look at this one over here. Let's look at 2x squared. If I look at the table for 2x squared, and let's go back to what we kind of did in Algebra 1, where if they gave me, and this should say f of x here. Again, the same x values of -2, -1, 0, 1, and 2. In Algebra 1, we would take this -2, and we would plug it in and then run through our order of operations, right? And evaluate that. So what's -2 squared? What's -2 times -2? 4. And then multiply it by 2, I would get 8, right? Okay. I'm going to do the same thing with -1. -1 squared would be 1 times the 2 out in front is 2. 0 is going to give me 0, so I'm just evaluating these. I'll do it quickly for us. And we get those y values, right? Does that make sense? These x's are the same, right? -2, -2. How does that y value right there and that y value right there relate? Is the 8, how much bigger is the 8 than the 4? It's double, right? It's twice as big. And it's twice as big because of that 2 right there that was in our formula, in our function rule, okay? So here's my question. What if I would have asked you to graph f of x equals like 3x squared? And you know that on x squared you have -2, -1, 0, 1, and 2. And on x squared, so on that function, x squared, circle too much, x squared, you know you should have these ordered pairs, right? You should have those y values. But what does this 3 right there do to all of these y values? It's going to make them 3 times bigger. Does that make sense, everybody? So I'd have -2, 12, -1, 3. I'd have 0, 0, 1, 3, and 2, 12. I'm just taking these y values from my parent function and making them 3 times bigger. Okay? You can see that in our work here. If I go, write f of x equals x squared. Okay, and then I'm going to say, well, what does it look like if I take c times f of x? And let c be any number I want. I'm just going to put some lines in here to make a comparison of points. So just give me a second. All right, so what I've got here right now is my parent function, which is the green one. So that's just x squared, right? 2x squared is the red one. Let's look at some nice ordered pairs here. For my parent function, I've got this. Let's make this really, so I can remember that's my parent function. So that's my parent function. If I look at the ordered pair, it's 2, 4. Well, how does that ordered pair relate to the ordered pair at 2, at the x value of 2, on 2x squared? Isn't the 8 twice as big as the 4? That makes sense? And that multiple of 2 is from that right there in my function. Okay? And that should be true no matter where I go on this graph. So there I'm at 3, 9 on the parent function. So then it should be 3, 9 times 2 is 18. So 318 on that graph. Does that make sense, everybody? And that should be true all the time. Okay, even like right there. Take that number, multiply it by 2, you get that number. Okay. Is that okay with everybody? So when I multiply by a number out front, it's going to make it grow. If that number out front is bigger than 1. So here I've made it 3. So on my parent function, I have 3, 9. So on the next one, I'm going to have 3, 27. Okay, now get that back to 3. There you go. So 327. Okay. How can I make, so when I multiplied by 2 or 3 or 4, it made something grow, right? It made the number you're thinking about in your head grow. How can I make that number you're thinking about in your head shrink? Okay, something less than 1. Now, we just got to be careful because, like, if I multiply by, like, -5, it will make it grow, but it'll also change the sign. So when we say less than 1, we actually want something less than 1, but bigger than 0. Okay, so if I want less than 1, bigger than 0, so think about, like, multiplying by a half. If I multiply something by a half, what's that the same thing as dividing by? It's dividing by 2, isn't it? So you guys, so when we multiply, it grows. When you multiply a number by something, it grows. When you divide, it shrinks. Okay? And what we're going to want to do here is make sure that the number when we say we divide, it's essentially we're going to multiply. But we're going to multiply by a number between 0 and 1. So if I make my C value something between 0 and 1, okay, so there's the parent function. Okay, now, and we'll go to this point here, 2, 4. If that's my parent function, and my number out front is like 1/2, so you see right here, my number out front is 1/2, right? How do the y values change? So that 2, 4 was on the green parent function, and now on the red function, I get 2, 2. So that 2 right there in the y position is half of that one. If I would make it like 1/4, which I can't do with the way I got it set up, so let's go 0.25 increment. So if I go 1/4 as my C out in front, you see that number 4 gets multiplied by 1/4, and it becomes 1. So this is a horizontal compression. Okay? So I want to show you something here real quick. This is the way I remember. I'm not saying this is right or wrong. But the way I remember what is happening, like, because they're going to ask you they're going to give you that parent function, and then they're going to give you that red one, and they're going to ask you what happened. What was the transformation? Okay? Well, I like to think about this red one here, or this green one, I guess. If I put my hands, if you put your hand right there and right there, and then put your foot like right there. Okay, so I had a rope earlier. So it's this idea. So my rope here is my parabola, right? Okay, got my hands where I put those X's. I got my foot. Okay, so right now I got my parabola, right? If I lift my hands straight up, okay, that parabola now just got kind of skinnier, right? Does that make sense? Okay. Think about this. If you were to put your hands where I've got these red X's and you pulled up, can you see that it's going to, so even if you put, can I grab that? So let's say you put your hand right there where that X is and you pulled straight up, it's going to go right there, right? And it's going to take that green curve and make it into the red one. So we stretched it vertically. Is that okay with everybody? If you put your hands on those red dots okay, put your hands on these red dots and now push down, your green curve is going to kind of do that, right? It's kind of like a bow out, and that's called a compression. Does that stuff make sense? Kind of visually. They're going to ask you in your homework, from time to time, they'll give you like a generic function. They'll just say, here's f of x. Okay, if that's what we start with, what does 2 times f of x do? Okay. My thing is, I struggled, especially early on, I always struggled with what they meant by this. And what they mean by f of x is that it could be x, it could be 2x, it could be x squared, it could be square root of x, it could be, the logarithm of x, it could be 2 to the x, it could be any function that you could come up with, any rule that you could come up with, okay? So this symbol here is standing in for all of these different graphs that we could be talking about. Does that make sense? Well, if I substitute then for one of these, and I like to always substitute x squared because that one, I think the parabola is the easiest thing to kind of visualize. If I put like 2x squared in there, well, what is 2x squared? What does that 2 do to x squared? It's going to be a vertical stretch. Does that make sense? Okay. They're going to ask you, if you start with f of x, what does f of x plus 3? What does that plus 3 do? Well, again, if I started with x squared, I know what that looks like, and then I add 3 to it. You guys remember that that's a vertical shift up? Okay. So they're going to ask you those kind of generic questions about particular functions. They might ask you, let's go back to this here. Okay. So remember yesterday we were talking about this graph being f of x. Okay, and I gave you those ordered pairs. They might ask you, okay, well, what does, if that's f of x, what does 2 times f of x look like? And that 2, remember, is it's going to increase your y's by a factor of 2. So this point here, the y value gets multiplied by 2. So the y value is going to become 4. So I'm going to have a point at negative 4, 4. This one here, this y value, you might not be able to see my cursor very well. This y value here is 0, 5 is going to get multiplied by 2. It's going to go to 0, 10. This one here is going to go to 3, 10. This one here is going to go to 3, 6, or sorry, 4, 6. And this one here is going to go to 7, like 16, all the way up there. And then if I connect those, you get really, it's almost, oh, I missed the point. It's roughly the same image, but you see how it's kind of elongated, it's stretched. Okay, does that make sense? Okay. So they're going to ask you to maybe do that with generic functions. You guys have any questions on anything? Does this make sense a little bit? I think transformations is one of the harder things that we will do, okay? Because there are so many rules to them. It's hard. Some of those rules seem very similar. It's just a slight positioning of like a constant. Do I put it in the parentheses? Do I keep it outside? Do I put the minus inside the parentheses? Do I keep it on the outside? How does that change then x's or y's? It gets confusing. But if you guys can understand the nuts and bolts of that, that's what I'm looking for. Okay. I'm going to stop there. You guys can finish up that assignment 2.6. And I believe that chapter 2 review is still open as well. So you guys can work on that stuff. You can ask me questions. You can ask one another questions. Tomorrow, we're going to move on to something a little bit different.